created by Mindstix Foundation Trust. Hello, students, and welcome to today's Explainer. We have a truly fascinating topic ahead of us as we explore the science of lenses. We will be going through 5 main areas today. 1. Introduction to lenses. 2. Anatomy of a lens. 3. Rules of ray diagrams. 4. Convex and concave images. And 5. Sign convention and formula. Let us dive right in.
Section 1. Introduction to lenses. Let us start with the basics. Now, you have definitely seen lenses in everyday life, right? In your reading spectacles, door peepholes, maybe even telescopes. Fundamentally, a lens is just a transparent medium bound by 2 surfaces. Notice the convex lens on your left. It is puffed up outwards, making it much thicker near the center than at the edges. Now compare this to the concave lens on the right. See how it curves inwards? That makes it thinner at the center. Both of these surfaces are actually parts of a sphere.
Section 2. Anatomy of a lens. Let us get familiar with some key terminology.
To truly understand how lenses bend light, we first need to learn the language. Please pay close attention to this first definition. The optical center, which we denote with a capital O, is the specific point inside a lens on the principal axis where light rays pass straight through without changing their path. This is an absolutely crucial fact. When a light ray strikes this exact point, there is no deviation whatsoever. It just goes straight through. Next, we have the principal focus. We denote this with a capital F. Now, when light rays travel parallel to the principal axis, they behave quite differently depending on the type of lens. For a convex lens, these parallel rays come together or converge to a single point on the axis. But for a concave lens, the rays scatter away from one another, meaning they diverge. If you trace them back, they appear to be coming from a specific point on the axis. That specific point, in both cases, is the principal focus. Let us trace these paths together. Notice the top diagrams. See how the incident rays pass directly through the optical center O without any bending at all? Now look at the bottom diagrams. Watch how the parallel rays hit the convex lens and converge exactly at a single point. That right there is a converging lens. Conversely, look at the concave lens. It scatters the rays outwards, but if you trace those dotted lines backwards, they appear to meet exactly at the focus. The distance between the optical center and this principal focus is what we call the focal length. Section 3. Rules of ray diagrams. We have 3 main rules to remember.
These established rules dictate exactly how light refracts through a convex lens. There are 3 fundamental rules we use to draw our ray diagrams, so let us go through them slowly. Rule 1. When the incident ray is parallel to the principal axis, the refracted ray will always pass through the principal focus. Rule 2. When the incident ray passes through the principal focus, the refracted ray emerges parallel to the principal axis. Basically the reverse, right? And Rule 3, which we just discussed, when the incident ray passes through the optical center, it goes straight through without changing its direction. Now let us visually verify these rules. In that first diagram, the incident ray comes in parallel, and the refracted ray neatly passes through the focus. In the second, the ray goes through the focus first and then emerges perfectly parallel. And in the third, the ray hits the optical center and travels straight through. Keep these patterns firmly in your mind, students. They are the essential building blocks for finding images. Section 4. Convex and concave images. Now we apply those rules. Let us put our rules to the test and see exactly what kinds of images are formed. Let us trace an actual image together. We place our object, let us call it AB, on the left side. Applying our rules, the top ray travels parallel to the axis and refracts right through the focus. A second ray goes straight through the optical center. Now, where do they intersect? They meet on the other side to form our image. Because the light rays physically meet here, this is a real inverted image. And if you look closely, you will notice it is smaller than the original object. Now, I want you to pause and think about this for a moment. What happens to the position and the size of this image if we start moving the object AB closer and closer to the convex lens? Take a look at this data. Notice the clear pattern happening here. When the object is very far away, at infinity, the image is just a tiny point. As we move the object closer, the image moves further away on the other side and grows larger. But look very closely at the last row. If we place the object extremely close to the lens, between the focus and the optical center, the image flips to the same side. It becomes magnified, and crucially, it is now virtual and erect. Now let us contrast this behavior with concave lenses. You will be glad to know the table for concave lenses is much simpler. Regardless of where you place the object, whether it is way out at infinity or anywhere between the optical center and infinity, the image formed is always virtual, always erect, and always smaller than the object. A concave lens never forms a real image. Section 5. Sign convention and formula. It is time to speak the mathematical language.
We have made some excellent visual observations so far, but in physics, we must codify these observations into strict mathematical language. To do this, we use the Cartesian sign convention. Just think of the optical center of the lens as the origin 0, 0 on a graph. The principal axis is your x-axis. According to this convention, the object is always placed on the left. All distances measured to the right of the origin are taken as positive, while distances measured to the left are taken as negative. Similarly, distances measured vertically upwards from the principal axis are positive, and distances measured vertically downwards are negative. By strictly following this sign convention, we can use the lens formula. This formula beautifully shows the mathematical relationship between the distance of the object from the lens, which we denote with a small u, the distance of the image, denoted by a small v, and the focal length of the lens, denoted by a small f. The formula is simple. 1 by v minus 1 by u equals 1 by f. I will leave you with this final, very important thought. The lens formula is exactly the same for any spherical lens, whether it is convex or concave, and for absolutely any object distance. So why is it absolutely necessary to strictly apply the Cartesian sign convention every single time? Think about it. Because, students, the mathematics will only reflect the true physics of the real world if we respect the directional rules of light. Thank you for joining this explainer. Until next time, keep observing the beautiful science all around you.